Okay, I'll be talking about group theory and providing an analogy to help you understand group theory. What is group theory? It's a field of abstract algebra that studies groups as well as the symmetries inside the groups. Well, what is a group? A group is a set of elements and a operation that follow a set of four main axioms. And those axioms are closure, associativity, identity, and invertibility. The closure axiom states that if A and B are two elements in set G, then the product or sum or whatever you get after performing the operation on A and B is also another element in C. The associativity axiom is basically the associative property. So if you group X and Y and then add Z, it would be the same as grouping Y and Z and adding X. Same with multiplication. If you multiply X and Y first and then multiply Z, it comes out the same as multiplying X to Y and Z. The identity axiom states that there's an identity element I in the set which doesn't alter the other elements in the set when used in the operation. And as an example, in addition, the identity element would be 0, because if you add 0 to something, like here is x plus 0 is still equal to x. When you add 0 to something, it doesn't change that element. In multiplication, it would be 1. Multiplying something by 1 doesn't change it. 1 times x is still x. The final axiom is invertibility, and this one states that every element in the set has an inverse or reciprocal of it that will make it the identity element. And if we're using addition as an example, x plus negative x would equal to 0, which is the identity element. So here, negative x would be the inverse of x. And in multiplication, the reciprocal of x would be 1 divided by x. Multiplying 1 times 1 divided by x is equal to 1, which is the identity element. If the set of elements and the operation, which doesn't have to be addition or multiplication, it could be anything else. It could even be like a function like f of x is x plus 1. As long as the transformation between the elements in the set is defined so it's consistent throughout each transformation, then it counts as an operation for the set. So if the set of elements and the operation conform to the closure, associativity, identity, and invertibility axioms, then it is considered a set. Sorry, a group, not a set. And groups don't even have to be numbers. They could be something more abstract, like shapes. Like, for example, we have a triangle here, and you could rotate it 120 degrees each time. And each rotation of 120 degrees would be the transformation. And it's consistent between each time, so that means it's okay to use in the set. And if we're using this triangle as an example, we could say that the identity property axiom still applies, because if it's part of a group, all four axioms still have to apply. So what is the identity element in I for this triangle? Well, it would be either turning it 360 degrees so it ends up in the same position, or it would be not turning it at all, because then it ends up the same way as it started and nothing has changed.
So every finite group is the graph of an automorphism group of a finite undirected graph. And an automorphism group is the group of functions from an object to itself which preserve the structure of the function. So there are two main types of groups. There's abelian and there's non-abelian. So essentially, abelian is like refers to the commutative property. So if a two elements within a group have undergo an operation, and the order does not matter, gives you the same results, then it's abelian. If the order does matter, and if you put them in a different order, you get a different result, then that is a non-abelian group. So there are examples of finite groups. Some of them are cyclic groups, and cyclic groups are groups generated by a single element. There are symmetric groups, and symmetric groups are the groups of all permutations on a symbol n, on n number of symbols. And there are alternating groups. And alternating groups are the groups of even permutations on a set of length n. So even permutations are permutations that come in pairs, and there's an even number of them. So there are 5 types of finite simple groups. A simple group is a group whose only normal subgroups are the trivial subgroup of the order 1 and the improper subgroup consisting of the entire original group. So these 5 things depicted here are the different types. And the first is a cyclic group of integers which have a prime group order, and a group order is the number of elements within a group. The second is the alternating groups of a degree of at least 5. The third type is a Lie-type Chevalier group, and Lie-type groups are groups with the structure of a manifold. And what a manifold is it's a space, a topological space that is locally Euclidean. And examples could be like a torus. Yeah. And then the fourth is Lie-type, which is a twisted Chevalier group. And then there's also the final type, which is a sporadic group. And sporadic groups are basically the 26 finite simple groups that don't fit into any of the 4 previous categories, so they have their very own.
Okay, to help you understand groups, let's think about a clock, except instead of a 12, let's say it's a 0. If we modify the clock like this, so the numbers read 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, then we can think of it as a group. The set for the group would be the numbers on the clock, which are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And the defined operation for the group would be addition modulo 12. And what modulo means is you would divide by 12 and then take the remainder. So for example, addition mod 12, let's say we have 13 and we apply the mod operator to it with 12. So 13 mod 12. You would divide 13 by 12, and then the remainder is 1 over 12, so it would return a 1. So under these specifications of the set being 0 through 11, and the operation being addition mod 12, which means you add first and then apply modulus 12. This clock could be seen as a group. So let's start by going through the 4 properties. First is closure. Any 2 elements on the clock, which are the numbers, added together will give another element on the clock. So let's say we add 2 and 3. That sums to 5, which is still on the clock. And 5 modulo 12 is still 5 because it's less than 12. So that works. But if you have a larger number, like let's say we had 10 and 11, that adds up to 21, and 21 mod 12 returns a 9. So it works for all the numbers in this set. Okay, the next that we have to check would be associativity, which again is the associative property in math. To check this, we just have to prove that grouping of elements doesn't matter when we're performing our operation. So let's just say we have 2 plus 4 and plus 11. This adds to 17, and with mod 12, it becomes 5. And then if we did 11 plus 4, and then added the 2 separately, that still sums up to 17 with the mod is 5. So we can see here that the associativity axiom still works in this model. The next one would be identity. So you can think about this two ways. It could either be 12 hours, because let's say we start at 1 and add 12 hours. Well, if you add 12 hours to 1, you'll be back at 1. But you could also just say you're not going to add any hours, so it could also be 0. So that's the identity element does exist for this. And then finally, each element can be added to reach 12, which we said could be the identity element. So 1 plus 11 is 12, 10 plus 2, 9 plus 3, etc. So that proves the inverse axiom works. And because all 4 axioms are fulfilled, this clock with a 0 instead of the 12, and addition mod 12 as its operation, can be considered a group.
Okay, so generally speaking, their group study is the study of symmetry. So there are many applications for group theory and finite groups. So in modern physics, it would not exist without group theory, because like the conservation laws in physics are related to symmetry of physical laws under various transformations. So laws of physics are unchanging over time, and this characteristic is invariance, which is in group theory. And this invariance under translation in time has led to the concept of conservation of energy. And then so in modern particle physics, particles were discovered through group theory, like they were predicted before they were experimentally found. And also in chemistry, molecules and crystals have structures and behaviors that depend on symmetries. So the concept of group theory is an important tool in chemistry. And of course, symmetry is related to the mathematical field of geometry. So this group theory is also used there. And for finite groups, there are some other applications too. So there is error correcting cyclic code. And this cyclic code is a block of code that is useful for detecting and correcting errors. There is also many coding, theoretical proofs, and performance estimation calculations that rely on finite group theory. And because the arguments are based on symmetry, the symmetry rules that come about in group theory. And there's also something called a Mollin series, which is a generating function that counts the homogeneous polynomials of a given total degree that are invariants for group G. And because it has to do with invariance, it is concepts from it can be learned in group theory. So group theory overall is very useful, and its uses span across many fields.